Hi, class. This is our first lecture in Chem 2B. You're looking at San Diego Reservoir at Columbia College. And in the background is the library. That's called Tamarack. And the upper floor is the tutoring center. The lower floor is the library. So just wanted to give you that scene. So before we start, you should have a notepad so you can take notes, and a pencil, of course, and perhaps a calculator, because we're going to be working a worksheet. So for every class, every lecture that you watch, that's probably what you need: a calculator, a notepad, and the worksheets. So for today, I'm going to start screen sharing right away. But before I start, this afternoon, or Monday afternoon, I have an office hour. So if you have any questions, you can join a Zoom meeting. You would find the link on the website at on the Confer Now page. So let me start my screen share. I want to first show you the schedule. That's right here. And I'm also going to turn off my video so I can move around a lot and it won't be a distraction to you. So here's the schedule for the course. So you can see today's lecture is going to cover chapters 12.1 and 12.2. See, this is the very first topic we're going to cover. The introduction and overview, that was a video that I posted earlier. So take a look at that if you haven't already. You'll find that on the homepage, and it's in big bold letters right at the top. That's the first video. That's the one you want to look at. So today's lecture is going to be on chemical reaction rates and factors affecting reaction rates. We're going to be using worksheet number 1. So you can find that in the module for this chapter. You'll want to probably download that, print it if you have that available. And so you can just see it or take notes on it while we go through this lecture. The next lecture that you'll look at, rate laws and integrated rate laws, is going to be using worksheets 2, 3, and 4. And we'll be covering the sections 12.3 and 12.4 in the book. So before you even view the lecture, it might be helpful to actually read the chapter sections first, chapter 12.1, 12.2, very briefly, just so you get familiar with some of the words that we're going to use. You know, this study of chemistry is going to be like learning a new language. There might be several new terms that you haven't heard before. Secondly, this is the worksheet we're going to go over. So be prepared. You need some preparation before you view the lecture, I think, to make it most beneficial. Especially take some notes. All of the exams, I'll just give you a heads up for the exams. The exams are all open book, open notes, open worksheets. They're going to follow the problem sets that you do in the Newton-Alta homework. It's going to be a Newton-Alta exam. So then I can possibly throw in a couple of custom-made questions. I haven't decided to do that, but that's a possibility. But so any notes, any worksheets, you should take notes when you're doing homework also. That'll all help you when you take the exam. So let's get started. I'm going to switch over to the PowerPoint. And so I'll change my share. So this is the first PowerPoint slide. So this chapter 12 is called kinetics. Kinetics has to do with the, you could think of it as a chemistry of motion, what's going on with the molecules. So it's kinetics, you know, has to do with energy of motion. And so when we talk about kinetics. We're talking about some, some kind of motion having to do with chemistry. So there are actually four major topics in this chapter we're going to cover. One is reaction rates. So that's really what kinetic means. It's really the study of chemical reaction rates, how fast reactions go. The second thing we're going to talk about are rate laws. These are equations that we can design to describe what's going on with a chemical reaction. And again, there's a thing called integrated rate laws. So we'll go from rate laws to integrated rate laws. Today we're going to do reaction rates and rate laws. And then half-life. So when you have a rate law, you can talk about half-life. We'll talk about what a half-life is. You've probably heard that term before. And then we're going to use an equation called the Ringis equation to calculate a reaction parameter called an activation energy. You might not have heard of activation energies before, but we're going to look at how to calculate activation energies from reaction rates. The very last thing we're going to do is briefly talk about catalysts. So today's topic is found in chapters 12.1, 12.2, and I said you should probably have read those briefly before you even watch this video lecture. You probably want to read it again afterwards and see if your understanding has improved after watching the video. In this section, we're going to learn about the definition of a chemical reaction rate. This is section 12.1. Know the definition of a chemical reaction rate and calculate reaction rates from graphs of chemical reactions. From section 12.2, we're going to learn about factors affecting reaction rates. This is an example of a chemical reaction. So we have two beakers on the left side and two beakers on the right. And when the contents of these two beakers on the left are mixed, a reaction is going to occur. The chemical reaction that's going to occur on the left side and the right side is the same one, but there's going to be a difference. And so this little note at the top says, notice how long it takes for the reaction to occur. So that's what we're going to see. So I'm going to start this and we'll just see what's going on. Okay, the solutions have been mixed at about 4 seconds. I'm moving the cursor along with the scroll bar. So if you look at the bottom of the slide, you can see the time it's taking. And after about 20 seconds, you can see that the beaker on the left of the chemist is starting to get a little cloudy. That's because a white precipitate is forming. And after, it's getting very cloudy. It's almost opaque now. You can't see through it. So probably after about 40 seconds, the reaction's complete. What about the beaker on the right side of this chemist? It's just barely starting to get cloudy. So clearly, even though it's the same reaction, the reaction didn't occur at the same rate. So a good name for this, the difference is that these two reactions are occurring at different rates. And a rate always has a time component. So time is really important. It's almost like how fast your car is going. It's like a speed. If you talk about how fast your car is going, you always describe that as miles per hour. It's distance over time. In a chemical reaction rate, it's some other parameter that you can measure over time. And so time, when you talk about rates, time is always the, I guess you could say, it's in the denominator if we were writing a value. It's something over time. It's something measurable over time. So let's see. Whoops. What's going on here? I don't know what this is. Okay, so the second thing on this slide, why did these react at different rates? Well, that's what we're going to talk about when we get to the end of the section, in section 12.2, what factors affect reaction rate. So there's a little suspense here. We'll wait until we get to that to talk about that. And how could we express the time it takes for a reaction to occur mathematically? Well, that's what we're going to get into next. So here's another picture of a reaction looking at the maybe at individual molecules. So this is a generic reaction going from A to B. There's a clock at the top that has the time component, and at the bottom is underneath the time component are pictures of the molecules. So we're going to start with all A molecules, and then after a certain time, maybe 10 seconds, some of those A molecules have turned into B molecules. And as we go on, the number of B molecules increases and the number of A molecules decreases. So what would that look like if we plotted this? Well, that's what it would look like. So the A molecules are going to decrease and the B molecules are going to increase. So that's typically how you would show a chemical reaction graphically. Now, in this case, we're measuring the number of molecules over time, but there are other values we can measure when we're doing chemical reactions. Typically, it's concentration. So you're going to see lots of, as we go through this chapter, you're going to see lots of graphs. And usually it's going to be the concentration of the reactant over time. And in a chemical reaction, the reactants, if a reaction occurs, the reactants always go down, right? The reactants are changing into products. So the curve for the the curve for the reactant is decreasing, always decreases. And the curve for the product always increases. So if you look at a graph of a chemical reaction, if the plot is increasing, that's a plot of the product. If you don't know anything else, if it's increasing, it's the product. If it's decreasing, it's the reactant. So concentration is one. Concentration can be measured, usually measured in molarity, which is moles per liter. The time can be seconds, minutes, hours, any time unit. The other things you can measure are values that are related to concentration. And when you do this in lab, you're going to measure absorbance or transmittance of light. So you're going to have a reactant or product that is going to absorb light. And you can have an instrument called a spectrophotometer that you're going to put the reaction mixture into. So it's going to measure the light transmitted or the light absorbed as the reaction progresses. So on the vertical axis, instead of number of molecules or molarity, you're going to have absorbance or transmittance, and that will measure the light absorbed or transmitted of the product or the reactant. And that value, the absorbance or transmittance, is directly related to concentration. So ultimately, what we're getting back to, anytime you do a kinetic study, you're really measuring the number of molecules that are changing. But there are lots of ways to determine that. Clearly, we can't really count molecules, but if we can measure the concentration, we know concentration is moles per liter. Moles are the number of molecules per liter, so that's one way to do it. If you're using a spectrophotometer and measuring absorbance, there's a equation called Beer's law, which relates absorbance or transmittance to concentration. So I think that's what you'll be doing in lab. So let's look a little more at this. So the reaction rate is the slope. It's how fast, it's how the change, if we look at the reaction rate of the reactant, we'd say the rate is equal to the change in concentration of the reactant over the change in time. And so we have values here for the change in concentration on the left side And we have values along the bottom for the change in time. So any change in concentration divided by the corresponding change in time will give you the reaction rate. Now, this sign in front of the rate, the change in concentration over time, is a negative for the reactant because the curve is going down, okay? Because the slope of this, so this change in concentration, change in time is a slope. It's rise over run, right? Change in, it's a rise over run and slope. So if we look at the change in concentration or change in time for the reactant, that's a negative slope. But rates are always positive. So to make sure the rate's positive, we have to put a negative sign in front of the slope for the reactant. If we're measuring if we want to get the reaction rate from the product, then the rate's going to equal, it's going to be positive, it's going to be the change in the concentration of the product divided by the change in time. So that increases all the time. So let's look at how we would calculate a reaction rate. And actually there's three kinds of reaction rates. And this is where you want to write something down. I'm going to switch briefly. Let's see if I can do this. I'm not sure if this will work. I guess it's not going to work. What I'm going to have to do is let me stop my share. And there's my notepad. So there are three, I'm going to write down the here's my notepad. Okay. There's three kinds of reaction rates. There's the initial reaction rate. I think you can see that. Tell me if you can see that. Maybe you can't. Let's see. So I can see it. I think if you change your view, if you can't see it, make sure you're looking at the gallery view. If you look at the gallery view, you can see my other, my notepad. And so there's the initial reaction rate. There's another kind of reaction we can measure called the average reaction rate. And there's a third reaction rate we can measure called the instantaneous reaction rate. So there's the three reaction rates. So the next portion of this slideshow, I'm going to illustrate how you determine those three different reaction rates from a plot. So we'll go back to the share screen. Okay, so the initial reaction rate is determined from the slope from the very beginning of this plot. So you can see I've drawn a line here, a tangent line from the very beginning. So it's tangent to this curve. And to make this calculation easy, what I've done is just drawn a line starting at the beginning of this reaction, draw a line as carefully as I can that's tangent, and then draw it all the way down to the time intercept. And so to calculate this initial rate, what we're going to do is we're going to take the change in concentration from the beginning, which is 40 molecules, from the start of this tangent line to the end of this tangent line, and then we'll divide it by the change in time from the end back to the beginning. So we're looking at this delta over here in the equation. The change in concentration is the final concentration. So what that would look like, and I'm going to switch back again to my my notepad. You can see it now. So the delta A, I hope you can see this, the delta A is equal to A, the concentration, we'll call it the final, or the second concentration, minus the concentration initial. So I hope you can see that. And the delta T, the change of time, is the change, the time, the final time minus the initial time. So in this particular initial concentration, so this is our rate, this is our initial rate. I'll put a I down here. So our rate initial is going to be, I think you can see this. I hope you can see this. Rate initial is going to be the final concentration, which was 0 molecules, minus, remember this is, there's a negative sign here, negative sign in front of all this, okay? We'll put a negative here. So it's the final concentration, which was 0 molecules, minus the initial concentration, which was 40 molecules. And this is, remember these values are taken from the tangent line. It's not from the, it's actually from the graph. It's from the tangent line. So that's important. Divided by the final time, which was 40 seconds, minus initial time, which was 0 seconds. So when we do that, we get minus 40 over, we have minus 40 over 40. So that means our rate, our initial rate is equal to 1 molecule per second. So that's how you would write that. So our initial rate is going to be 1 molecule per second. So I'm going to go back to my screen share. And let me see how I... And here's the PowerPoint again. That's how you calculate the initial rate. So let's look at the next rate. So that's called the average rate. In this average rate, what I've done is I said, let's determine the average rate between 10 seconds and 50 seconds. So again, it's the same thing. We have to we have to calculate the difference in concentration of A between 10 and 50 seconds divided by the time between 10 and 50 seconds. So the change in concentration of A is going to be about 9 minus 30 approximately. So if we go 9 minus 30, we'll have minus 21. So the delta A is equal to minus 21. And then if we have 50 minus 10, that's the delta T, which is 40. So we have minus 21. So our rate is equal to minus 21 over 40. So that's equal to about plus 0.5 molecules per second. So what we can see is that, well, our average rate between this time, between 10 seconds and 50 seconds, is a lot slower. That means this slope that we've written, this line that we've written between these 2 points, is a much shallower slope than the initial slope. You can see our initial slope line was like this. Our line between these 2 points is like that. So it is shows a much slower rate. And that's what happens to reactions, is that the rate slows down as the reaction proceeds. And that kind of gives us a clue that one of the major factors is the concentration, the way the reason why it slows down is because there's just fewer molecules to react as the reaction progresses. The number of reactant molecules disappears. So that's what happens in chemical reactions. The rate slows down as the reaction proceeds. It's not constant. There's one kind of reaction, as we get into integrated rates, that we'll see there's one type of reaction where the rate doesn't change. It stays constant the whole time. But otherwise, for most chemical reactions that are studied, the rate slows down as the reaction progresses. So that's the change in, what's the matter? In time. Excuse me, the change in concentration of A, and this is the change in time. Okay, the third rate that I want to talk about is instantaneous rate. So the instantaneous rate is the rate, the slope of the line tangent to a particular point. So in this case, I've drawn a line that's tangent to a point at 30 seconds. So a point in time. So just pick a point in time along this curve, say 30 seconds, draw a line tangent to the curve at that point. And again, to make it simple, I've drawn a line that intersects both the y-axis and the x-axis. So it's easy to determine the difference in concentration of A and the concentration of, or the change in time. So the change in concentration of A, if we look at this, I won't use my notepad, I'll just talk about it, is 0 minus about 32. So we get the delta A is minus 32, and the delta T is 60 minus 0, which is 60. And so our rate, again, is about 0.5 molecules per second. So this instantaneous rate turns out to be about the same as the average rate that we calculated before, which was kind of in the middle of this slope. If we check the instantaneous rate at 40 seconds and drew 10, it would be slower. If we check the instantaneous rate at 50 seconds, it would also be slower. The instantaneous rate at time 0 is the same as the initial rate. So here's a different reaction. This is a reaction of, we have a compound called butyl chloride, C4H9Cl, plus water is going to butyl alcohol, C4H9OH. And we've got a time, this is a table rather than a graph, but on the left side is a table of the times that the concentration of the C4H9Cl, the butyl chloride, was determined. So at time 0, the concentration was 1.1 molar. At 50 seconds, the concentration was 0.905 molar. On the right-hand column is the average rate determined in each time interval. So we've got average rate in the 0 to 50 second time interval, an average rate in the 50-100 second time interval, and so forth. So if you look at these rates, again, as I said previously, the rates are decreasing. So the concentration is decreasing because we're measuring the reactant, but the rates are also decreasing. And at the bottom here, I show the calculation of the first time interval. So the rate, because it's a reactant, is a negative change of concentration of a reactant over the change in time. And if you look at that first interval, we have 0.0905 molar minus 0.1 molar divided by 50 seconds minus 0 seconds. So if you follow this calculation through, we end up with a 1.9 10 to the minus 4 molarity m per second. Molarity per second, if you're measuring concentration change, is pretty typical. So this would be an average rate. We don't have to just pick these small time intervals. You can measure an average rate over any time interval. You could do the whole reaction. You could start from 0 to 800. And you can do that time interval. So there's a bunch of average rates. So average rates just depend on what time interval you choose to calculate the average. There's only one initial rate, but there are lots of average rates, and there's also lots of instantaneous rates. So an instantaneous rate would be taken at a particular point in time. So this chemical reaction is bromine plus formic acid, produces bromide ion, 2 hydrogen ions. This produces hydrogen bromide and carbon dioxide. So on the left-hand side, here's the table of data. So this shows the table converted into a graph. So it has the two kinds of presentations of kinetic data that typically are used. Tabular data on the left showing a column with the time and another column with the concentration of the reactant. We have two reactants here. So we could do this reaction or measure the rate of this reaction by following either reactant. So in this case, these chemists have chosen to follow the change in concentration of the bromine. So the bromine's decreasing. You get a curve of the concentration of the bromine versus time shown in the graph. In this particular graph, they've taken tangents at a point in time of 100 seconds. They've taken a tangent at a point in time of 200 seconds and tangent at 300 seconds. So they measured instantaneous rate at those three different times. And you'll notice that the rate is going down. So the rate is the change in concentration, which you could estimate here. You draw a line over to the y-axis. It looks like it goes from we had a 0.007 minus 0.009, maybe 95, something like that. And then the change in time would be if you drop the vertical down to the time axis, you would get a change in time from something like 120 minus 50 seconds or 60 seconds, something like that. Okay. So that's one. You could do it graphically. You know, if you that's another way you can determine the rate. Would be mathematically using an equation. So one thing to notice is that the rates are always decreasing. All right. The average rate. So the average rate's a change in concentration over time, but that would be picking two intervals. And we have, like I said, the delta means that you're doing the final concentration minus initial concentration over a final time minus initial time. Okay, a few more definitions of those different kinds of rates. Okay, so here's our first worksheet, and I think we'll do this at the end. So I'll come back to the worksheet. This is what it looks like. This is the graph we're going to analyze. There are several questions associated with it, so we'll come back to this. But one of the questions you can think about this is what kind of rate are we measuring in this particular figure right here? So with this tangent, what kind of rate are we measuring? So think about that. Okay, there's another thing about in a chemical reaction is that I said you can measure the rates from either reactant, if there's more than one reactant, or from the products. And there's a relationship that has to do with the stoichiometry, so these coefficients. So the relationship between the rates. So we have one rate, the rate's always positive. If it's a reactant, it's minus 1 over the coefficient times the change in concentration of the reactant over the change in time. If we have a second reactant, again, it's minus 1 over the coefficient of that second reactant times the change in concentration over time. And that's equal to 1 over the coefficient, positive, for the change in product concentration over the change in time, equal to 1 over the coefficient change in product concentration over time, if there's more than one product. So if we go back, let's go back to this reaction. So in this reaction, we had bromine reacting with acetic acid going to bromide. Actually, let me look down here. Maybe there's a sample. No. Okay. Yeah, let's go back here. Okay. So I'm going to switch to my notepad here. Here's my notepad. So in this reaction, I'm going to abbreviate. We had bromine plus acetic acid, HA. I'm going to put HA for the acid. So bromine plus HA is going to 2 bromide, Br minus, plus 2H plus CO2. Okay, that's what the reaction was. So the rate then, the rate of bromine is going to be minus the change of Br2 concentration over the delta T. That's what we showed in the graph. That's how they were determining the rate. But if we wanted to know, well, what's the rate of formation of the bromide ion? Because we can calculate it from that. So the rate of the bromide ion is going to be 1 over 2 times the change in Br minus over the change in temperature. So if we want to know the rate of the bromide ion, the rate of the bromide ion is this value. It's the delta Br minus concentration over the delta T. So we have to relate that to the rate of bromine if we want to know the rate of the bromide ion. So let's rearrange this equation. So let's look at this part of the equation. And we want to relate the rate of this, of the bromide, Br minus, to the Br2. So if we rearrange that, it's a pretty simple rearrangement. If we multiply both sides by 2, we end up at minus 2 times the change in Br2 concentration over the change in time is going to equal to the change in Br minus concentration, and I kind of messed up my, over the change in time. So it shows that the bromide rate is going to be double the bromine rate, the Br2 rate. Okay, so that's how you do it. So we would start with this relationship, and you can write them for every reactant. So we could write this relationship of rates for every reactant and every product in this equation. And then if the question is, well, how fast is CO2 forming? Well, if we look at CO2, it has a coefficient of 1. It's the same coefficient as the Br2. So the rate of CO2 formation is going to be exactly the same rate as the Br2. It doesn't say Br2. Br2 looks like this. Br2 bromine. Okay. Okay, so let's go back to the video. I'm going to share my slide again. So screen share. Okay, oh, here it comes. There it is. Whoops, what happened to it? Come on. All right, so here we are. Okay, so here's the relationships of the rates of the reactants compared to the products. Rates decrease, so they have negative sign, and products increase, so they have a positive sign. So that's the end of section 12.1. So here's another reaction. I want to show this reaction here. And in this case, the volumes of the reactants looks like they're double of what they were previously. So let's see how long this reaction takes. Let's see, the chemists mixed them together. The reaction is going 22 seconds, 25, let's see. So it looks like this reaction is taking about the same length of time as the previous reaction, even the previous faster reaction, even though the volumes are double. So let's see what that means. Oh, here's another reaction. Let's look at this one. Okay, that was a double bond. Here's the volumes. Oops, what happened? There we go. Diluted one of the reactants with water. So in the previous slide, the reaction, even though the volumes were doubled, the reaction rate seemed to be about the same as the faster reaction rate previously. In this case, we're already up to 40 seconds, and the reaction still hasn't occurred. Really slow. Okay, so I'm going to stop. So why is that? Well, you saw at the beginning of this one is that the chemist added some water to the solution. He diluted it. So that's a clue that maybe concentration has something to do with the reaction rate. We've already talked about that as the reaction proceeds, it slows down because the concentration of the reactants decreases. So let's look at some factors that affect reaction rates. So one of those is the type of reactant, and that has to do with where it is on the periodic table. So typically, if two compounds are reacting together and they're on opposite sides of the periodic table, let me put a periodic table here. Periodic table under my notepad camera. And let me switch to that. It's my notepad camera. Try to make it a little bigger. Made it bigger on my screen. I don't know if I made it bigger on your screen. But if you look at a reactant from the left side of the periodic table, from this side, and react with something on this side, well, it usually you get a very vigorous reaction. If you react things that are in the middle next to each other, it's not quite as much of a reaction. In fact, metals don't really react together. Metals react with nonmetals. Nonmetals will react together, but usually don't get a metal-to-metal reaction. Okay, so unless the metal's in a compound. So if this is metal, this is in a compound, then they'll react together. But otherwise, if you mix magnesium and sodium, nothing's going to happen. But if you mix magnesium with chlorine, boy, you get a very vigorous reaction. The elements in the same column, remember, they have similar properties. And so the like lithium, sodium, potassium, rubidium over here on the left side, the alkali metals, they're going to have similar reactivities. But the reactivity of the alkali metals is going to be widely different from the reactivity of the iron family of metals here in the transition metals. Okay, so the similar or elements in the groups have similar reactivities. And an element in, say, in the alkaline earth column is going to have a reactivity with the halogens. Well, all the alkaline earths are going to react similarly with all the halogens. So it's going to be a similar type of reaction. It might not be as vigorous. Usually as you go down a column, the reactivity of the element increases. So I'm going to go back to my screen share. And back to my PowerPoint. So reactants and their physical state. So the physical state is whether they're solid, liquid, or gas. And then also where they appear in the periodic table. And elements in the groups are all have similar reactivities with other elements in other groups. The physical state, so one important factor that we'll learn about later when we talk about collision theory is how fast molecules in the atoms are moving, how much kinetic energy they have. And so you learned previously that the kinetic energy has to do with the temperature and also the physical state. So gas molecules have much greater kinetic energy than liquid or solid molecules. So molecules in the gaseous state do have quite a bit of reactivity because they're moving faster. The difference is that the concentration is much less. So the concentration of the molecules in liquids and gases, in liquids and solids is much greater. So those are different opposing factors. So because kinetic energy is important, temperature has a great effect on the reaction rate. So at higher temperatures, reactant molecules have more kinetic energy. So that's important. That has to do with collision theory and kinetic theory of reaction rates. We'll talk about collision theory a little bit later. Concentrations of reactants. And lastly, catalysts. Catalysts speed up reactions. We're going to talk about catalysts also. So let's see, the physical state, besides solid, liquid, gas, there's also another factor called, if you have solids, especially for solids, that the surface area of a solid changes the reaction rate. So the smaller the particle size of the solid, the faster the reaction rate. So a solid reactant that's in the dust state, which the particles are really small if it's a dust, was going to react extremely way faster than a solid reactant that's, say, a big crystal, or a big block. So, for example, if we just talk about, it's not a chemical reaction, but it's a physical change of state. If we talk about ice melting, ice chips melt a lot slower than, a lot faster than an ice block. And so if you think about in the case of a solid, if you think about how much surface area there is, the more surface area, the much faster the reaction. Oh, there we go. Surface area of a solid reactant. There you go. Oh, the pressure of gaseous products. So we're going to talk pressure later about pressure. And pressure is directly related to the number of molecules. Greater the pressure, the greater the concentration. If you remember the ideal gas law, there's a relationship between pressure and N, which is the number of moles. And so we're going to look at how later on in this chapter, how you can relate pressure to reaction rates. Actually, that's in the further, we're going to talk about equilibrium later on. So that's where pressure comes in. So that's the end of the slideshow. What I want to do now is just go to this worksheet and do a couple of problems on it. So we'll switch to the worksheet now. And I think if you can maximize that, I've got it maximized on my screen. I wonder if I can make it even bigger. Made it bigger on my screen. It's not bigger on your screen, but I think that's okay. So let's go over this worksheet briefly. So on the right-hand side is and I hope you have this worksheet in front of you so you can see it. On the right-hand side is a list of tabular list of the data, time data and concentration data. I'm not sure, it's not very clear. I don't know why that is. And on the left-hand side is a graph of that data. There are a few questions to answer at the bottom. So is this a reaction profile for reactant or product, and why? I think you can answer that. You followed the discussion previously. So I'll let you answer that one yourself. What kind of rate is calculated from the tangent in the above figure? So this is something you just circle: initial, average, or instantaneous. You decide what that is. Let's see, find the average rate between 0 and 600 minutes and 3600 and 4200 minutes. Does the rate increase or decrease? Okay, so I'm going to do one of these, and then you're going to do the other one. Oh, then there's also explain. Explain why the rate either increases or decreases. So is this for a reactant or a product? I think you can answer that. So let's look at the data. It says to calculate the rate between 0 and 600 minutes. So let's see, do we have, I'll do, so 0 to 600 minutes is right over here. So the rate between 0 and 600 minutes is going to be this change in time. So this is the delta t here. And this is the delta, supposed to be a bracket. This is the change in, I guess we're looking at the concentration of oxygen in its moles per liter, the change in O2 over here. So the change in time is 600 minutes. Is it minutes? No, 600 seconds minus 0 seconds is equal to 600 seconds. And the change in oxygen is 0.0021 minus 0 seconds, which is equal to 0.0021 moles per liter. That's our molarity, moles per liter. And so our rate is going to be, our rate for that time interval, remember, is going to be the delta oxygen concentration divided by the delta T. And so we're going to have 0.0021 divided by 600. So the rate is going to be 0.0021 divided by 600. So our rate, average rate, I'm going to use my calculator here, is 0.0021 divided by 600. And that comes out to be 3.5 times 10 to the minus 6. So we get 3.5 times 10 to the negative 6. And the units are, I'm just going to change moles per liter to molarity per second. And another way they write that sometimes is molarity seconds to the negative 1. Okay. Okay, so here's our rate right here. Here's our answer over here. Okay, so that's for part 1. I'll let you do part 2, which is calculate the average rate between 3,600 and 4,200. Should be seconds, not minutes. Yeah, it's seconds, sorry. I'll put seconds here. Okay, and then we'll see if the rate increases or decreases. That'll be interesting. Second one is calculate the instantaneous rate at 1200 seconds and 4800 seconds. So I'll do the 1200 seconds, and I'll let you do the 4800 seconds. So 1200 seconds is right here. So here's 1200 seconds down here. So I'll put a little, so this is where we want to calculate the instantaneous rate, right there at 1200 seconds. So I have to draw a tangent. So let's see. So the tangent would be something like this, you know? It's not perfect tangent, but it's kind of look, when I draw the tangent, I look for the space on this side of the curve to be the same as the space on that side of the curve. So tangent looks something like that. So what I like to do is so you draw my tangent and maybe intersect a couple lines here. So at least it makes some of these. So my tangent's like this, the tangent. So my concentration, here's a concentration over here. So my concentration on this particular tangent line is here. That's the final. And this is the initial. So I have okay. So let me move this line. So here's my final concentration. Here's my initial concentration. So the final concentration is 0.005 molarity. The initial is 0.002 molarity. So my delta O2 is 005 minus 002. I can do that one in my head. That's 0.003 molarity. All right. The change in time, so the time, I'll have to drop a line down here to get my initial time. So my initial time is going to be something like this right there. So the initial time is about, I'll say 600 seconds. So right about it. And my final time, then here's the other line is here. So my final time is going to be about right there. So I'll drop the vertical line down there, and I do that. Pretty good. That looks to be about, the difference is 1200 seconds in between these marks. So that's probably about 1800 seconds. So my delta T is going to be 1800 minus 600, which is 1200 seconds. So I have my delta T's and my delta O2 here, so I can calculate my rate. So at 1200 seconds, my rate instantaneous, is going to equal the change in concentration, which I figured up there was 0.003 molar divided by 1200 seconds. So my instantaneous rate at 1200 seconds is going to be 0.003 divided by 1200. And that comes out 2.5 times 10 to the minus 6. 2.5 times 10 to the minus 6. Okay, so what do we have? Let's see, 5 minus 2 is 0.003. 1200 seconds, 600 to 1800. That's 1200. 2.5 times 10 to the minus 6, right? So that's, oh, that makes sense. Okay. The average rate that I did before was at the very beginning, the first interval. That was 3.5 times 10 to the minus 6. And now my instantaneous rate at a later time is 2.5 times 10 to the minus 6. That's slowed down. So that's correct. That makes sense. All right. So that's it. So that's the worksheet. That's the lecture on sections 12.1 and 12.2. So go back to the video and I'll stop my screen share. Let's see, stop it. Stop, come on, stop screen share. Let me see if I can do that. I don't want to share it. Oh, no, I don't want to share it. Okay. So I'm not sure how I get out, but anyway, you can see me there. So that's the end of the lecture. So took about an hour, so it's pretty long. So hopefully I'll get faster on these. So good luck. Just a reminder, I have office hours at 1 o'clock on Monday. So if you have any questions about this, just check in. Okay, goodbye.